Hello class, and welcome to the Chapter 6 lecture of our C++ class. So today we're talking about I/O streams. So now we gain a little bit more utility with C++. We are now able to read into programs, and we are able to, write out from programs and store to and read from files. So now we have more data permanence. So we can kind of expand our programs. Utility really grows here because we can store our data to disk, which is non-volatile, and we can read this data later, and we can modify the data as needed. So, we're kind of on a step. We're really only one step away from storing information to databases. Huge databases where we can store massive amounts of data and retrieve massive amounts of data. So we're really becoming, useful here with our C++ programs. So, overview streams and basic file I/O. So this is, reading from streams and writing out to streams. And, a stream is something like, input from the keyboard, or from a file. And, an output stream would be considered, what you see on the screen or writing to a file. Tools for stream I/O. So now we're talking about formatting, kind of how this input and output looks to us when we display it or when we write it out. And character I/O. So when we go through, and this isn't just ints and doubles, it's actually, right, strings and characters to our output streams, which, again, would be, to the display or to files, utilities for dealing with this on a character by character, on a string basis. All right, so starting off here, basic. So, of course, I/O is input-output. We should all know this by now. Okay, and input as well as outputs are driven by streams. So, really what this means is that, streams of data, characters at any particular time could come in or be written out, to and from streams, as well as, integers, doubles, any object or any data type. So this is why we call them streams. And again, as I said, common input types are a keyboard or a file. And, for output, generally, standard output, which is a screen or a file is what, write to with these streams. Streams are objects. I don't want to, obfuscate. I don't want to confuse things too much, but they are objects, and there's a reason that we are just mentioning this. Don't dwell too much upon it. Just know that objects have their own functions that operate on the objects. And if you read the the C++ PowerPoint, kind of from a historical perspective, the history PowerPoint, you'll see that C++ was designed based on the previous C language, kind of in an object-oriented fashion. It does a whole lot more than that, but one of the things that was added to it was object orientation, this concept of objects. All right, so, again, a stream is the flow of data. We saw, or I mentioned why that's the case. Any piece of data could come in, any piece of data could be written out, for input or output streams. Input stream is to the program, so this is from the perspective of the program. So, input stream, we're getting data into the program. It's driven from the keyboard or from the file into the program. And output streams, the most common types are to the screen, the standard input, we do that via cout. From the keyboard, we do this via cin, or, we can write out to a file. So yeah, as I said, the most common are cin and cout. Cin is input from the keyboard. Cout is output to the screen, to the, the standard output. We need to use the I/O stream directive for this, and that's no surprise to us. We've already seen this. Okay. You can also declare your own streams. Okay. There's more than just cin and cout. Files. We use files. We use streams to interact with files. As I said, we have this concept of data permanence, data persistence. Okay. Files will keep the data on disk. It says permanently here. I don't agree with permanently. Disks get corrupted, etc. So anyways, we have more persistence, more kind of true persistence here. Okay, it lasts beyond the end of the program. RAM is volatile. Disk is not. Input file can be used over and over, correct? So we kind of have our data sitting there. You don't have to retype it every time. And yes, as I said, you can deal with much larger volumes of data. Again, when we get into database connectivity, which is not in this class, we have even larger, really, amounts of data that can be stored on disk. We have terabytes and terabytes, or even petabytes of data, really, depending on the application you're using. All right, so file I/O. So when we read data from a file, we take input from it. Yeah, from beginning to end for now. We can stop before the end. We can start at any point. We can skip around within the file. We have the concept of file pointers, so we kind of can point to any location in the file and read from this particular location. But for now, we're going to be reading from beginning to end, baby steps, right? Okay. No backing up. Well, not right now. We certainly can. Like I said, we can adjust these file pointers, point to any particular location in the file. But for now, we're just reading from beginning to end. Okay. When we write to a file, again, for now, we're writing from the beginning to the end. Again, this isn't true, but we're not going to be backing up for right now. We're just going to go from beginning to end. All right, so streams. We'll give you a quick example here. We'll give two examples before we jump in. Actually, we'll jump in with examples if you think of it that way. All right, so what I've done is declared two stream variables. Notice I included the file stream directive. That's what's necessary if we're dealing with files. I've declared an input stream variable as well as an output stream variable. Okay, this is what we need if we're reading in from a file and if we're writing out to a file, respectively. I'll leave that for now, actually. So we just declared two streams, an input file stream and an output file stream, right? Okay, initialized. Well, we didn't initialize this yet. Okay, so we're going to go ahead and initialize these. Sorry, just got a new keyboard here. Make a lot of mistakes with it. All right, so what I'm going to do is open this input stream. Okay, when I initialize it, I'll open this file with the input stream. So this is kind of initializing a file stream. So I'm opening a file named file.txt. Now I have put this file. If you look, my home directory is my working directory, anyways, is C users pbrooks documents. So if I go into my documents, here's my file.txt. And what I did, I populated it with two ints and then two doubles. Okay, so now I've initialized this input stream, and this way I have kind of a handle to this file, file.txt. So I can read from this file. What I'll do is I'll declare two ints, and I'll declare two doubles as well, or any kind of float really would work. Now, how do I read from this file? Well, remember it's a stream, and you know how we deal with streams, right, if we're getting input from CN. So what I'll do, stream name, all right, input operator. There we go. Okay. That's how we read from, and we'll go ahead and prove that this works. So what I'll do is kind of parrot out the contents of this file. There we go. So there it is. Okay, so we're kind of going piecewise here. All right, so we initialized them. All right, and yes, the value of the variable can be thought of as the file it's connected to. And you know, that's a good point, because what I did here is I referred to my stream instead of my file. Well, you know, referring to my stream, the stream is really the only handle to the file that I have. So, you know, when we refer to the stream, we're referring to the file that we've opened and that we're working with in that stream. So a stream variable can have its value changed, and that just means opening a different file. That's all. You would close that file and work with another. Okay. So, you know, we're not going to harp on this too much. You know, a stream is a type of object, and objects have their own functions. And this really is only said here, this is kind of only mentioned on 12, so that we don't kind of blow your mind when you see the different kind of function that we're going to see shortly. Okay, so we just saw an input stream, right? IF stream, input file stream, IF stream. That's what kind of stream my input stream is. Okay, so we have to include the file stream directive. The standard namespace is also necessary. Streams. So we see we initialize, you know, we kind of declare, rather, excuse me, an input stream by, you know, declaring its type, by putting its type, and then the, you know, the actual variable name of the input file stream. So this kind of declares an input file stream. When we initialize, you know, that's when we actually open a file. Okay, output streams are basically the same thing, only it's OF stream, output file stream. You could see I declared an output file stream right here named my output stream. Okay, I've already included file stream header, so you know it did the compiler. That's why the compiler didn't gripe at me. Okay, it does require the standard namespace, and you see the declaration is OF stream for output file stream variable name, and that's what I did here. Only I named mine my output stream. So as far as connecting to a file, you saw that. So whether it's input stream or output stream, the syntax is the same. You know, the stream name dot open, and then within parentheses goes the string representing the name of the file on disk. And this is relative to your working directory, to your present working directory. You know, that's why I placed my file.txt in the present working directory. Okay, and yes, we saw that we can use, you know, the extraction for the output, the input, the output operator. Okay, so what this one does here, this declares two ints, one number, another number. Apparently, this input stream is connected to a file containing two ints because we read from it one number and then another number. So it has two ints separated by white space. You know, white space means non-printable characters, as we see, or as we will see. All right, output stream, same thing. We'll go ahead and show you output stream. So I'll create a new file. And I say create a new file because if the file doesn't exist, it should create it. Called fileout.txt. And really, instead of just displaying to the screen, what I'll do is I'll write out to this output stream object that's connected to fileout.txt file. So I will write out to the fileout.txt file. Let's write this stuff in reverse order just for fun. So what I would expect to see in this fileout.txt file is basically 5.678, 1234, 5678, 1234. To make sure that this compiles here. Oh, you know what? I put C out. I should have used the name of the output stream. C out is an output stream. So is my output stream. Okay, so they are both output streams, but I need to use the file output stream, my output stream. All right, so let's make sure that we have this file created, fileout.txt, and it contains, oh yeah, all right, 5.678, 1234, 5678, 1234, and you see I forgot to put white space between them. Lesson learned. So I should have done something like that. And surely you can mix, you can mix strings, ints. You see here we have a string and int, a string and int, and double. It doesn't matter. Writing out is writing out. Just as with C out, it is to a file output stream as well. External file is basically a file on disk. Okay. Yeah, it needs to match the naming conventions in your system. This is kind of obvious here. Your path needs to match everything. File needs to exist, especially if you are opening a file. So this is a good point. After using a file, you should close it. Now, if your program terminates, normally you should close that file. At least C++ should close the file for you. However, it is always good programming practice to close that file when you are done working with it. If you don't and your program crashes, especially while writing, but if your program crashes, before you close the file, there's a chance that it could be corrupted. Then you've got problems. Yeah, see, closed files will reduce the chance of the file being corrupted if you have, if your program abnormally ends. When we say abnormal, we mean, abnormally ends, abnormally terminates. And yes, this is true. You need to close the file before you, before you read from it, or before you write to it. Try to write to it in a different place. So again, with objects, so input stream and output stream do have functions associated with them, and they're seen a little bit differently than the functions that we've seen so far with the dot operator. Input stream and output stream, they both have, they both use open function. As we can see, I have input stream.open and I have output stream.open. So they're a little bit different versions because this is for, this is the input stream version and this is the output stream object version. Right? And a member function basically belongs to an object, is a function that operates normally on that particular object. And, objects can have several different types of functions. Okay. Objects are instantiated from classes. Don't worry too much about the details now, but a class is a user-defined type, and it has its own data types, its own primitives, as well as it can contain other objects. Objects come from classes. Okay, so input file stream is the actual class, and in stream is actually instantiation, a variable of that class. Okay. The class of an object, of course, is going to determine its member functions because objects have different members depending, depending on what class they come from. All right, a little bit more on on classes here. So every variable declarative type IF stream or OF stream have the open function. Again, as we saw, input file streams and output file stream, open functions are a little bit different behind the scenes, but as far as we see them from the programmer's perspective, they pretty much do the same thing. They open a file. Now, here's what we're getting to with the several previous slides about objects and classes. And this is just so we don't blow your mind when you see this. We call this open function a little bit differently. We don't just call the function. It doesn't consist of just the function name and then the parameter list inside the parentheses here. What we do when we call a member function, we call the object, and then we use the dot operator, and then we call the member function. So we would call open on this particular input stream on the in stream object. You see, this way we can associate a function call with with a particular variable, right? Otherwise, if we just called open, you wouldn't really know what we're associating this open call with. I suppose you could pass something like, pass in stream as one of the arguments in open, but that's not the way object orientation works. We use object name dot and the function. Object dot function name and then the argument list, the parameter list within parentheses. Now, when we open files, if they don't exist or if there's a disk error, any one of a number of things could happen. It may fail, and so you will need to check for an opening failure before you continue. Otherwise, your program may behave kooky or it just may crash. Okay, and you see here, the file might not exist. The name might be typed incorrectly, which really would mean that the file doesn't exist, right? Because the name you typed doesn't match to anything on the disk. So yeah, we have a fail on this stream object, be it input or output. We have a fail member function, which would return a Boolean. It returns a Boolean true if the open call failed. Otherwise, it returns false, which means, hey, it opened, it's okay to proceed. So yeah, when we fail to open a stream, we generally want to stop. If we're about to perform some sort of action that could cause problems or that we can't proceed with, we may want to halt the program, to stop the program instead of continuing and pretending as if nothing bad happened, or worse yet, trying to write to a stream that doesn't, is not associated with a file. All right, now when we do this, we have this little exit function. Okay, an exit takes an integer argument. So let me do this. We have an input stream object, so I'll just name something crazy that I don't have on my file system. Okay, and I'll show you good programming practice here. So what I'll say is if, we failed here in trying to open our file, we need to exit program. We need to halt it. We need to exit. And in order to do this, this is function of C standard library. So what I need to do is include C standard library. I include my headers. So now exit takes an integer argument. I'm not going to get too much into this. And this is really for programmers' benefit. This isn't really going to be visible externally. you have kind of a convention. You have either exit 0 or exit 1. Exit 0 signals a normal termination. Everything is fine. We just met some sort of criteria as we need to exit. Exit 1 means there was a problem. We're exiting because there was a problem. You know, generally this is only for the programmer's benefit, but it does take an integer argument. So I'll go ahead and run this. Uh-oh. So, you know, it's basically telling me, hey, we have a system exit call, right? Exit code for this process is 1. So, you know, I told my program, hey, if you know, opening the file doesn't work, there's some sort of problem here, and that's what we see paired out. So we have to include the C standard library. And yeah, exit is not a member function. So, you know, again, you have the two different types of function calls. You have a member function call, and then you just have kind of a library function call. Member function is a function that is associated with an object. It belongs, you know, object is an instantiation of a class. That function is a, you know, function associated with that class or with that object. So yeah, as we saw, you know, exit, excuse me, exit requires, you know, the pound include C standard library. And yes, most modern libraries will require standard namespace. And we saw this, you know, if we fail, then we exit. Okay, that's best programming practice. So when reading from a file, yeah, why would we include a prompt if we can't really, a file's not interactive, it can't respond to us. So that's, it may sound a little bit silly, but if it's there, it's because people do it, okay? And so now appending. When, you know, when we open an output file, we will obliterate the contents of that file. So watch this. If I run this program again and again, oh, actually here. So I'll run this program again and again. Here we go. All right, going. So I've run it a few times. Now, if we look at this, we opened a file named, or we created a file named fileout.txt. We wrote a line to it. We saw what this line is. Do we see several lines in this fileout.txt? Let's see. Fileout. No, we only see one, in fact. And you know why that is, because each time we open this file, we obliterate it. We kind of, when we write over our previous data. So that could be a problem if we just want to have a file that we, you know, continually forward to, which seems, you know, very logical to want. We'll have to include a flag to indicate that we are appending data to this file, that we're not clobbering it. Oh, sorry. So if we run this several times, go ahead and back. Let's go back and look at this file. Yeah, there we go. So we have several lines here. And you see what, here's a good point. You see what happened to this file. I have a bunch of junk written in there. Well, why is that junk there? If we look at this, I'm reading in from this file that doesn't exist into my ints and doubles. So there's still they're declared but not really instantiated, so they're full of garbage, right? They were pointing to, created in 2 ints and 2 doubles that reside in memory locations that have not been instantiated. Therefore, they can point to any kind of trash they want. So that's why I'm getting this weird behavior. So this is the, the function of the append flag. It'll write to the end of a file. And you can clearly see this. So now we've run it, 6 different times, and we have seven rows since we put that append flag in there. Right, yeah, again, if we're opening for output and it doesn't exist, we'll create a new file instead, a new file with that name that you're trying to open will be created. When you may want the user to actually input the name of the file that you're going to be working with, and you can definitely do this. Arrays will be studied more in Chapter 7 and the standard C string library covered in Chapter 8. But you can do this right now. And this is just kind of a quick overview of what you're looking at. You would need to declare a character array. It's kind of what we call a C-style string. This is an array that will hold 16 characters, right? Addressable 0 up to 15. This declares, of course, the array name is, file name. Okay, and we just input it. So we're declaring an array of characters named file name. We prompt for it and we input to it. We just use the extraction operator. We just get it from the input stream, standard input stream, and we open our input stream based on this file name. So we'll see an example here. Iterate all this. Right, we'll create room for up to 99 characters. Well, 98, actually. Actually, we'll make this an output stream. That'll make things a little bit easier on us here. All right, so you see I'm prompting for, any file name up to 98 characters. You have one for the, character array termination character. We'll find out about that next chapter. And we'll open a file with this file name, and then we will output some junk to it. Let's go ahead and run this. All right, so let's see, make sure we have this file name here in my working directory. There it is. All right, so that's kind of how we prompt the user for an actual file name and open that file name. Again, we'll understand a little bit more about this after next chapter. But know that this works, and there are some examples here and in the chapter. All right, so some kind of section end questions here. Writer program uses a stream called fin, which is connected to an input file, and fout, which will be connected to an output file. We've seen this. Go back to the examples. I have them. We've seen declaration, we've seen initialization, which is where we will open on a file name. We use the fstream header. It's a little typo there. Should be at least 3 members of an IO stream object. Yeah, sure. Open, close, fail, right? tools for Stream IO. Okay, so now we're kind of formatting our input and output. Now we're getting a little bit more useful with our IO, getting fancy with it. Okay. So, we can, determine spaces between items, how they're displayed, such as, the number of significant digits or the number of digits displayed after, in the mantissa after the decimal, as well as, whether you're displaying exponential notation or fixed point notation. Showing digits and how many of them after the decimal point, even if they're zeros, if they're non-significant. EOS will show the the positive numbers, show the plus sign in front, as well as the negative sign for negative. And you can left or right justify. Now, if you have a column of a certain width, you'll either push the output over to the extreme left or the extreme right. All right, so formatting output. We have setf, which is, set flag, and this is on any output stream. All right, we'll be able to set our flags. Now, our our setf function will take, an argument here. In this case, it's iOS fixed. We have our scope resolution operator. So we're saying, within scope of iOS, it's going to be fixed flag is what we're going to use. We also have show point. Now, what fixed does, it will always show the numbers in non-exponential notation. So even if it's a huge number, it won't show, to the powers of 10. It'll show the actual number itself as you're accustomed to seeing them. Okay, we have show point, right? Always show the decimal point. Kind of makes sense to us. We can also set the precision of our output streams. And really, this is kind of compiler dependent. It can either be 2 significant digits or it can be 2 digits after the decimal point, is what precision would show. So if you have, kind of 5 significant figures after the decimal point, it'll be truncated, the output will be truncated to 2. Otherwise, you will show, .00, or if it's .1, it'll actually show .0. It will extend the precision. Okay. Now, it's basically the same thing. What this is saying is that, cout and a file output stream, they're both output streams. They're both output stream objects, so they both have this setf and this precision member function. Okay. Yes, so as I said, this is kind of compiler dependent. So depending on what version you have, you'll show either 2 significant digits, 2, 1, 2, 1, 2, 1, 2, 1, 2, or you'll show 2 digits after the decimal point, 2, 2, 2, 2. I believe with MinGW, you're showing 2 after the decimal point. So we'll go ahead and look at here what we just did. Yeah. So here in MinGW, actually I'm showing, we have 24.334. We're actually just showing 2 significant digits overall. We're not worried about, the mantissa. So that's, the MinGW compiler. I think I have 481. This displays 2 significant digits overall. So I was actually wrong. Okay, and yeah, the calls for precision will only apply to the stream named in the call. And when we say the stream named in the call, we see that I set precision on this stream, which is an output file stream connected to, you know, 1234.txt. Okay, so everything, you know, all those flags or any flags that I would set, I only set, you know, one here. I only set the precision actually. You know, applies only to 1234.txt to that particular file because it's connected to the output stream, which I set the precision. All right, so we have the flag iOS fixed. You know, it's a member function, set as is as well as precision. So yeah, fixed will avoid exponential notation, you know, the kind of the scientific notation, the exponential notation. So if we make this some huge number, let's make sure I didn't make mistakes. We'll reuse my file so I don't clutter my documents directory. It's already actually pretty cluttered already. So you see the effect here. All right, so first, I wrote out a huge, monstrous number, and I wrote it in scientific notation, right? Because it's more convenient to say, you know, 1 times 10 to the 12th, which is, you know, 2, 6, 7, 10, 12. Yeah, that's correct. So kind of it lessened the precision on this number, and it wrote it in, you know, an exponential notation. Then I said, hey, I changed the output stream and say, you know, only show in non-scientific, you know, non-exponential notation. So when I rewrote the same number, it actually wrote the number without, you know, the scientific notation, without exponential notation. Show point. This will always show the decimal. You know, if you write a floating point number, you'll generally only get 3. And actually, we can even really, we can even set the flag on, you know, on an output stream to on cout. But we'll go ahead and continue writing the file. So if we declare a double named DBL, we'll say it equals 3. We'll go ahead and output that double to the file. Then we'll change the way we display it. We want to show the decimal point always. Now we'll come back and write this thing again. So we'll show the difference between, you know, how it's output. And this would apply again to cout. So this would apply to the standard output what you see on the terminal as well. Okay, let's go back to our file. All right, good. So you see it's written as an integer. There's no need to display that decimal point in the zeros, right? But if you really want to, always want to show the point, decimal point. Show point flag will convert this, or will you know, we'll put the decimal point there on and show the trailing zeros. So it almost looks as if it's converted to, you know, a double from an int, but it's not. It's still a double floating point value, double precision floating point value. It just shows the decimal point with the trailing zeros. Creating space. So you can set the width, right, on the output, and you can do this, you know, to the standard output or to a file, and set the width, you know, by using the width member function along with the, you know, the actual width you want to use for the number. Okay, so if your number takes up less space than your width, you'll be either right or left justified. I believe the default is right justified. We'll go ahead and see this. Set it like they had in the example. Yeah, we see the output is right justified. 1, 2, 3, and there's our 3 on the right side, the right side of the column with 4. Now, if we want to change that, we can say, we can set the flag and say, hey, left justify all this stuff. And we'll come back in and look what we did. Yeah, there we go. So default is right, or you can force it via the iOS right flag. And when I set it to left, we are left justifying in that column with the 4 characters. So we still have kind of 3 blank white space characters over here to the right. Yeah, here's a good point. So if you specify a width that is less than the width of your number trying to put in, let's say you specify 3 and your number a whole bunch, right, 7, the entire item is output. It's not truncated. The entire item will be displayed. So don't be surprised if you specify a width smaller than the width of the item, that it will print the whole item out. Yeah, just as we have set flag, we also have unset flag. All right, so if I come back in here and I say, oh darn, no. I come back in here and say unset flag. iOS left, then I would expect to see, by default, 3 on the right. Then since we set the left, 3 on the left, and then since we unset left, 3 on the right again. Make sure I see that. Hold on just a sec. Let me figure out what happened here. Okay, so I'm back. I'm not sure. I'll look more into this particular flag, but what I did is I just swapped it out for the show positive flag. So we should just see 3 output. Then we have positive 3 because I set the positive flag. Then I unset it, and then we should just see 3 again, and that's indeed what we get. We type in the file name here. So here's a working example, of what I was looking to show you. 3 plus 3 and then 3. I'm not sure exactly what happened here with the unset flag. I'll look into this more, but anyways, you get the point here. You can unset flags as well, and you can see it. So manipulators, it's a function call. It's basically it is non-traditional. They'll call a member function. Right, a member function belongs to an object, which belongs to a class, or which is an instantiation of a class. Okay, they may have arguments, they may not. So let's take a look at an example here. So for cout, what we can do is set width for, if we don't want to kind of permanently, or at least for the session anyway, set these flags, what we can do is use manipulators such as set. So we can set width to 4 and to display 10. That way we'll have 2 spaces after 10. And then set width to 4, 20. Set width to 6 for 30, so that way we'll have 4 spaces here. So that's one example. And this works for any output stream. Right? If we had an output stream named outstream, this as well. Set precision. Set precision. Remember, we use the output stream dot precision. Instead, we can use a manipulator set precision. So we can output the $sign, and if we want to use the precision, and on your compiler again, to be 3.0, for example, in order that would look better for a price. If your compiler sets the Mantissa precision to 2, you can do this, and this will output 1030, right? As well as here, it would output 2050. On mine, not so. Yeah, this is a good point. Like I said, if you use, if you use set precision like this, that setting is going to stay in effect until change. Okay, it's going to take effect in the session. And this is I/O manipulation, so it's going to use I/O manip library. So we'll take a look at this. We'll say, gosh, what are we setting width to? Actually, you know what? We won't follow their example. That's up here. They have set width to 4. We'll make it something big so we can see the change. Oh yeah, look at that. So we got 9. 99 trailing spaces. I have 10. So what I would need to do, set 99 again, right? Set width as ephemeral. Yeah, there we go. So set width is ephemeral, being that as soon as I use it, it kind of resets. Set precision is not. So that's an example of using set width. It does. Again, this can be used for files as well. Okay, this isn't only, if you want nicely formatted files, you can use a whole heck of a lot of these flags or manipulators to format your file as you wish. And yeah, set precision is not ephemeral. Be aware. See. Yeah, it behaved a little strange on my function on my system because I don't have the show point displayed here for the 9. and there's a limited amount. Let's see, there's a limited precision that show. So there's a limited precision that will show. So 9.01, we get this funny rounding, and I actually addressed this in one of the discussions here. We get this because of the the binary nature of part of one of the problems of storing decimal values in binary. So this is why we get 0, 1 at the end, and why we get 9, 9, 9, 9, 9, 9, and 8 here at the end here. So this is kind of the max width we can display here in my system. Set precision flag is not ephemeral. Okay, it takes effect until it's reset. Yeah, again, IO manipulation library. I'll have to include the IO manip header. Okay, streams. If we want to pass a stream to a function, we can do so. Now, keep in mind, a stream deals with IO kind of at a low level, so it doesn't make sense to pass a copy of a stream. That doesn't do anything. Copy of a stream, what is that really? We need to pass by reference. So let's do this. We'll say file.txt we were working with, I think. Let's go ahead and obliterate it. All right, so I'm going to pass this output stream to a write function. Now, when I do so, I'll need to pass by reference. Oops, output file stream. I'll need to pass it by reference. Right, that's the only way it makes sense. Okay, so you see I'm declaring this output file stream as OSTR. I'm instantiating it. In other words, I'm opening it with a file name. We'll overwrite this file I already have named file.txt. I catch it by reference, and I write to it. So let's make sure this works. Compile. No. Let's see. Forbids declaration of, it's a void function. I just do stuff in return value. All right, and so let's take a look at file.txt. We should see 1, 2, 3, 4, 5, 6, 7, 8 with exclamation point. Yes. All right, good. So that works. So we pass file streams by reference. Okay. EOF, end of file. All right, so we know files aren't of infinite length. All right, and they can vary in length. We may not know the length of the file. Normally, won't in advance before we read it. Maybe if it's a an INI file, if it's a configuration file, we may know the length of it, but we can't assume anything. A lot of files we will not know the length. So we can use Boolean logic basically when we try to read from a file into a variable, we'll get a failure. It will return a Boolean. Every time we read in from a file, we'll get a Boolean. We get true if we were able to read the value into a variable. We get false if we weren't. So that's how we know that false is how we end file. In some files, there are end of file markers. There's -1, and really before that, there's a history. C and C++ actually write an end of file marker file. But normally, this is kind of a pseudo character. It just means the operating system says, hey, you've reached the end of the file. You're past the end of the file at this point. And that's how C++ knows to stop reading, is the end file marker. So here we go. So if we want, you see we have a file full of doubles in this example. If we want to kind of average the number, the doubles in this file, what we can do is say, as long as we can keep reading these numbers in, do it and add them to sum. Go ahead and increase the counter. Then when we're done, when we've read everything from the file, when this finally goes false, which happens when we reach the end of the file, then we'll go ahead and average our numbers. Okay? In fact, let's change our file.txt. Change it to 2.0, 3.0, 4.0, 5.0, 6.0. Save it. Delete all this junk we were doing. Clean house here a little bit. All right, so we're going to read in from this file. So we need an input file stream object, right? And we'll name it ISTR. We will open it. All right, and so we'll say while we can read in from this file. We'll read into double. So while we're able to read into double from this file, this double DBL, we will add to the total. Instantiate here. Then when we're done, I think this is right. I'll did it wrong here. Count. Oh, I named it counter. Again. Okay, something went wrong here. iStream.open. Oh, I didn't instantiate counter. So counter is full of junk. Let's try this again. I think that was the problem. So try this again. If not, we'll troubleshoot a little more. There we go, 3.5. 1 plus 2 plus 3 plus 4 plus 5 plus 6, so that's 1, 6, 10, 15, 21. 21 divided by 6, yes, it's 3.5. So that is right. Okay, and in the same vein, we can read, we doubles in, we can read ints in, we can character by character, C. So that's an example. Okay, so this is a little nuance here. For now, just place your directives at the beginning of the file or include directives. Don't worry too much about this. We're not going to have, flashing directives namespaces yet. So just go ahead and keep placing all your stuff at the top of the file, these pounding and usings. Well, usings you can put in the functions as shown if you like. That's harmless. Fairly harmless anyways. Right. As far as so this is a sample program. We've seen this. Yeah, we've seen this stuff already. We've seen use this stuff. You're invited to look at 6.6, 1, 2, and 3. This is a very long chapter, so we're not going to dig in. The output when the following line is executed. All right, so here's a little gotcha. Okay, so you'll see an asterisk, and then you'll see 1, 2, 3, 5. And the reason is, see the set width is set to 3, but 1, 2, 3, 4, 5 is wider than 3, so the whole number is displayed. Okay. Fixed will never show us scientific. It'll always show us, traditional number format. This is right justify. So is this. Maybe they meant to put left. Scientific will show exponential notation. That's that little e, with the power 10 after it. Show point always shows us the decimal. Show pos will show a plus in front of, positive numbers. All right. So now we're on character I/O. All right, so, sometimes we can read character by character if we want to read strings instead of numbers, or doubles, okay? Really, when we, output data to a file, as we can see, where's our file? As we can see, we have 3 characters here, 1, dot, and 0. Okay, so of course, that's composed of 3 different characters, just like they have here. Number 10 is composed of 2. Output and input would be done, kind of as 2 characters in a stream. And the interpretation, really how the compiler interprets these tokens, and even the program logic, if you're reading in character-wise fashion, you determine the logic as to how these are interpreted. Okay, but usually you'll just use the extraction operator, and that will perform an automatic conversion for you. Okay, C++ does provide for the relatively low-level functions. They don't auto-convert, and they'll allow you to interpret. So get reads in from an input stream character by character. Okay, even that white space that we talked about, character by character, it doesn't skip any white space. Okay, this is as opposed to the extraction operator. Units in at a time. It'll perform some, kind of some auto conversion for you. So here we declare a character called next symbol, and then we read the next character in from the standard input from the keyboard into this next symbol character. Okay. Now keep in mind when you do this from, when you're reading from standard input, it will also read the \n line character. And we'll see how to deal with that in just a bit. So, the syntax is kind of the stream name dot get, and then you actually, you'll have your variable that you are reading into. It'll read from the input stream into this character. Here you go. Right. So let's take an example. We'll see kind of example that proves the point here. Sorry, just a sec. Better make it gray. I'll allow for 900 characters. Here, I looks more like a loop. I'll just call it count. Actually, I don't like that. All right, let me take a peek at this here. So enter string, okay, single character, have my array. I initialize a counter. All right, so C should not equal \n until I'm done with my input. Get, I'll push it, into the, oh, no. I'll push character into the array. Yeah. Sorry, just a sec. Oh, actually, I see what I did. So I got to read into the character. That's what happens when you use variable names too closely together that are non-discrete. All right, so you see what I did here. We read in from the keyboard here, this cin.get, so get reads one more character in. So what I do is I prompt the user for a string, and I say, hey, up until this new line character, which is automatically appended when you press enter after entering a string from cin, from the keyboard rather, I'm getting the next character in the stream, and I'm pushing it into the next space in the array, and then I output the array. Hi there, hi there. Now, if I were to not do that, if I were to just get everything from the stream, we would see the \n is actually in the stream. So when we use cin.get, we want to be on the lookout for the \n, which remains in the input stream. That's what this is saying here. So yeah, your stream.get, and then the variable that you're reading into. Okay. This also works for files. We can, file.open in input stream file, really input file rather, .open the input stream, and we can open, the input file, and then read in from it. We can read character by character via get, successive iterative calls to get. Okay. Now, to prove the point, kind of to hammer the point home here, we have, code. We declare 3 characters, get all of them from cin. If we give, from the keyboard, if we give the input A, B, and then we press enter in C and D, remember that enter, that new line is stuck into the input stream. So character 3 will be \n, that line character. So again, hammering the point home. Okay, so this is a different way of doing what I did. I said, while the character is not equal to n, you see the character is not initialized. It's declared but not initialized, so it's kind of full of junk. They have a different way of doing it here. They use a do while loop. They wait until they read a character into it, so that they, know that there's a valid character in there, and then they compare to \n, and that's fine too. Okay. \n is a character. Actually, this is kind of written badly here. So it's a character, right? \n signals new line. Now this is a string. If you have double quotes, and within double quotes \n, this is not quite a character. This does not evaluate to a character. So just be aware of the difference between the two. There is a difference, although they're kind of treated, similarly. They look similarly. Okay, puts one character into the output stream, be that the standard output, the keyboard or a file. Cout.put 1 cout.put 2 cout.put 3. All right, so I should expect to see 1, 2, and 3 on the keyboard after I execute this. There you go, 1, 2, 3. And we can also write to a file this way. So if we were to declare an output file, and if I were to change this to output stream, since the output stream is associated with that file.txt, we will write 1, 2, 3 to file.txt. And since I didn't open it in append mode, I'm going to clobber that file. So we should just see 1, 2, 3 in file.txt after we execute this. Yeah, 1, 2, 3. Right, moving right along. Yeah, so we don't have to necessarily output a character literal. If we have a character variable with a value in it, we can simply put the variable name, in the parameter list here, because this will evaluate to the character. So here we have an example output stream. We declare it. We initialize it by opening a file, and we put, we write z out to it. Just did that. Put back. Okay, put back will put a specific character back into the input stream. So if you read up to, if you want to read up to a certain character, once you read a character, the file pointer will advance to the next position in the file. So if you have like a \n, let's say, you want to read up to a \n, but you also want your, your next iteration of reading of that file to that \n, then you'll use put back. Okay, that puts a character back into the input stream. That's the most useful example of put back anyway. So here we see, we read in from a file named, fn, or rather from a file stream named fn. Okay, so we're getting a variable into the character next. So as long as character next is not white space, always put too many spaces in here. We'll go ahead and write it to an output file, and then we'll go ahead and get the next character. All right, but once we get this space, once we encounter this space character, we drop out of the while loop. Okay. And we put this next character that we read, which is space, back into the input stream. So then the next time we read fn, we'll also get this space. Well, actually, see an example. Sorry, 3, then, so we read, we wrote into file .txt, be nice and close it, spin it in an input fashion. Now, oh, sorry. It's not doing much good with any display statements, is it? All right, so you see what happened there. So I read C1 in, which is going to be 1. I read C2 in, which is going to be 2 because it's reading sequentially in the file. Then it said, hey, put C2 back into the input stream. Then when I read C3, since C2 was the first character in that input stream, it read C2 in. So that's why we see 2, 2. And this can be useful in a few contexts. I'm not going to tell you how to use this because there's no hard and fast rule. It will depend on what you want to do. Okay, just know that put back puts the character back in the input stream to be read. All right. Okay, so again, this is, again, in the displays, you're encouraged to read and understand these. I'm not going to cover them too much since we have a very long recording here. Right. So yeah, as I said before, O stream and C out are both output streams. Okay, they're both output stream objects. They are subclasses of output streams. Rather, output file stream, excuse me. Output file stream and C out are subclasses of output streams. Output stream is the parent class, and C out, output file stream are subclasses. They have the same member functions. Okay, so that's why you see some similarities between C out and output file stream, as well as C in and the input file stream. Okay, we're not worried about inheritance yet. This is this is chapter 10, as it says here. Now, here's kind of the kicker. This is polymorphism. This is what we call polymorphism in object-oriented programming. You can pass an output stream object, which is the parent class of output file stream and C out. Okay, you can pass an output file stream or C out, and you can receive it in the function as an output stream object reference. And this will still work. This is called polymorphism, right? You pass it as the parent type. It will figure out at runtime what the object is. Okay. Right, compiled. Okay, and yeah, we pretty much saw this is a rehash of what we've seen. It's just it's an example, anyways. We're going to discuss. Yeah, simply pass name of the stream, receive it as reference. In this case, just input stream. So default arguments, you can have default arguments. And here's an example of a default argument. I'll come in here and I'll say, I'll just create a function called myfunc. It'll receive an integer, default value 7. So if we don't supply my function with a parameter, it's going to operate with the default of 7. So we'll issue 2 types of calls, and we'll say myfunc b. It will provide it a value, and then we'll call it without an explicit value. So if we don't provide an explicit value, I will take the value 7. Otherwise, it will take the value we pass to it. So I would expect to see 8 and 7 displayed on the screen. There you go. Okay. Multiple default arguments. Multiple default arguments are possible. Once you start putting in default arguments, let's say we have, multiple arguments here. We have 2. One of them is default. Okay. This is going to be an obligatory parameter that we have to pass. We don't have a default value for it. So if we just call myfunc without any values, it's going to gripe at us. The compiler is going to say, eh. Matter of fact, let's try this. Yep, nope. Too few arguments. Now we can do this, right? What will this do? All right, so our first call here we'll push the value 3 into our first integer. Since we don't have a second integer, we'll use the default value 7. So I would expect to see 37 displayed on the screen. Then, end line so we can differentiate these calls. Then I'm passing 2 explicit parameters. So I'd expect to see 3 and 5 displayed here since, the explicitly passed parameter will override default value. So then compile and link, and you should see 37 and then 35. Yes, voila, that's what we see. Now here's a little trick. It's not a little trick, it's a little gotcha. Watch what happens here. Okay, what do you think is going to happen? Okay, so we have a default. If I give it 3, gosh, how's the compiler going to figure this out? How's it going to figure out what it means? I mean 3 to be pushed into the default value, in which case we have an explicit value, let's say a variable of, parameter that doesn't have an explicit value, which is a problem. Or is it going to take the default value of 5 and then push 3 into the right-hand side? I don't know. Let's see. Yeah. Moral of the story, once you start putting in default values, the rest of your parameter list must have default values. Okay. Yes. So we're going from left to right. For this first call, I expect to see 3, 5, 7. For the second call, I expect to see, change this. So for the first call, I would expect to see 3 substituted for I, and then split 5 and 7. For the second call, since we're going from left to right, I'm going to shove I into 3, shove 6 into J, overriding the default of 5, and then I'll still display the default K 7. So I expect to see 3, 5, 7, 3, 6, 7, and then 3, 6, 8. Oh, yeah, I didn't display my variable there. Yes, 3, 5, 7, 3, 6, 7, 6, 8. Exactly. So that's multiple default arguments. And here you have an example where they, you have to provide an explicit value and one where there's a default. Again, 5 would be substituted here into arg1. And in this one, 5, 6, 5 would be substituted into arg1, and 6 would provide the default value of 2. This is a little programming practice, or rather a best practice programming. All right, so we'll see a little bit more about this. It is next semester. Next chapter. When you mix cin and cin.get, now remember cin reads up to \n. Okay, so that \n is put into the stream. So that's a problem because when we go to call cin.get after that, the \n is in our input stream, and that's what cin.get reads. So our cin.get function is pretty much ineffective. Okay. So there are a few things that you can do. You can call cin.get after a call to cin with the extraction operator. You can call it. You can call it, then call it again. You can use cin.ignore, which we will see later, and flush the buffer, which we'll see later. New line function from 6.7 can be used to clear \n. We'll actually take a look at this here. Just a moment. All right, so if we come down here to 6.7, yeah, so, go ahead and get here while symbol is not. So yes, is that correct? All right, so they call the new line auxiliary function. Aha. Okay, so new line just reads up to the next new line. Yeah, so there are a few different ways of discarding that backslash in it. Right? Base. Ah. Yeah, here's an example. So if you out it after that as, right? So EOF. Remember I talked about the end of file. Usually it's kind of a pseudo character. It's not a real thing, actual character. All right. So end of file will return a Boolean value. Now there is an end of file character, but in this case we can check for the end of file while while reading from an input stream simply by using EOF member function. So if we use the input stream name .eof, this will return a Boolean value. So it returns true if we reach the end of the file, otherwise it returns false. So what I can do, no, here. All right, so I'm looping through the file until I encounter the end of file character. So what I'm doing is I'm reading a character and displaying it. Oh, that's a semi. It's like I got a little shift happy there. Voila, end of file. Okay, and that's truly what I did. That's exactly what I did here. Okay, so input stream.eof returns true if we have reached the last character. In other words, basically saying while not EOF. In other words, becomes false when you read the past last character file. It's a little bit confusing here. I don't like this slide. Still true after, becomes false when. You just remember, end of file will tell you if you reach the end of the file. So this will be true if end of file. Okay, that's kind of a fancy way. We're doing character input. So this is one way of saying you've reached the end of the file. The other one is using the extraction operator. Remember, like we did before, reading in doubles or whatever until this while goes false. That's because we are at the end of the file. Okay. So EOF is when you're reading characters, and the other one is kind of an automatic extraction. You will get a Boolean false returned back to you. Okay. Sorry, just one sec. All right. So yeah, editing a text file. Again, read the displays and understand them. We're going to most of what we'll need here on this PowerPoint. This is a very long lecture. Okay, so CC type, the C character type. So this is kind of some character manipulation functionality that we have here. If you're familiar with Java, you know 2 upper and 2 lower. 2 upper, A, lowercase a will return uppercase A, and 2 upper, uppercase A will return uppercase A, since it's not going to modify it. We also have 2 lower, we have white space, we have a whole host of characters here. So you see we have different calls that we can make. They're actually the same call, just different assignments. So this just returns an expression. This could be the uppercase A, and it's sent to the output stream, the standard output stream that we view the terminal. This is actually an assignment to character C. Okay, to upper A places uppercase A, character C. Okay, and then we can see out at that point. Now here's a little gotcha. If you just see out to upper A, you're going to get the integer code. You'll get the ASCII integer code for this character. So be sure you know what you want to do. You may be best pushing this into a character and then displaying it, or you might want to go ahead and cast it, because watch this. We'll do this real quick so you see what I'm talking about. We have to include our C character type. Man, that was weird. 66, what the heck happened? Well, it gives you the integer, the ASCII integer value. So I can do this one of 2 ways. I can cast a character. Again, I'm using the older style cast. You can use static cast. Old habits die hard. Yeah, so, or I can, push this value into a character, and C++ will kind of convert that. This will also display. Oh, what happened here? Oh. All right. Is space it's a Boolean that will return true if what I'm looking at is a space, a simple space, or if it's tab, or even if it's new line, that's treated as white space as well. And again, there's a whole host of character functions. We haven't seen all of them. There are more in the book. All right, write code that will read a line of text and echo the line with all uppercase letters deleted. Well, what you can do is look for is upper. Again, look at the functions there in the book. You can look for uppercase, and you can copy from one character string to another, or rather from one character array. I guess it is a C string, one character array to another, and just simply not copy the uppercase values, that are found with the Boolean, is upper. Describe 2 methods to detect the end of a input file. Well, we saw that, EOF, individual characters will give true if you've reached past the end of the file. Otherwise, the extraction operator will go false once you've reached the end of the file and you can't read anything else in. And describe white space, it's right here. We saw it's a space, a tab, line. Okay, so that's it here. Sorry, this has been a really long lecture here. There's kind of a lot to cover, not a whole lot. It's not a real brain buster here. There's just a whole lot of information. Remember, this is a reference. You can always come back to your book and look at it. You have to know everything. I'm convinced nobody knows everything about C++. Maybe there's, 1, 2, 3, 4 pocket protector types that'll prove me wrong here, but you have your book and the slides and everything as a reference. Okay, so don't stress too much. Know this stuff. Practice it. That way, when you go back and look at it, you'll remember it easily. All right, that's it. See you in the next lecture.